All right, so today we're going to talk about intro to electricity. So we'll be talking about the history, the language, the structure of matter and atoms, electron shells, how to transfer charges, what the terms and forces and safety are. Now, I'll go ahead and say now, I'm a safety nut, guys. That's simply because I prefer everybody to go home safe at the end of the day. All right. So the history of electricity. So a lot of this stuff can be very interesting if you really start digging into it. So one of the things they have found in archaeological discoveries is they found something they called the Baghdad battery, which is essentially a jar that had almost like an electrolytic fluid, just like what you would find in a battery, that could actually had the power to run things. But then we hit the Dark Ages, whereby any and all technology was considered heresy. So thus we ended up dropping a lot of knowledge and only recently rediscovered it. So when they say it was discovered in the mid 1800s, that's kind of a misnomer. Modern electricity was discovered then, but electricity itself had been around for a little while. So we get electricity, 99% of the electricity we use on a day-to-day basis is done with electromagnetism, or magnetism in general. We'll talk more about that later. When you move current, which we'll talk about what that is here in a minute, when you move current through a wire, a magnetic field is created. And this is what this is all about what we use to power our lives. Any questions so far? All right. So language, we have several different things that we use. One is called voltage. You've probably heard this. At the very least, you've seen caution, this has extreme voltage, or something along those lines. So it's called two different things. You can call it voltage or you can call it EMF. Whenever you're dealing with military or certain aspects of this, the letter E is used. Most of the time, though, the letter V is used for voltage. We'll talk again more about that later. So current is electricity in motion. That is completely and 100% true. Static electricity, I don't know how many of you have ever done the rub your feet across the carpet and go zap somebody. That's static electricity, so it's at rest until you go and grab something, and then the charge jumps from you to it. Okay. By the way, does anybody know what you're supposed to do when you get out of your car to pump gas?
Turn your car off.
Well, you gotta turn your car off. Another good thing it's best to do is to discharge any and all electrical charge from yourself. So you touch the body of the car to discharge the static. Very good, Mr. Kane. So that's become a big thing on the stickers on some gas stations, is that I'm trying to see if I can show y'all a picture of it, but so this is something that's been put on a lot of gas pumps these days, it says touch your car, touch something, metal, to get rid of static electricity. It's not very good to put that on anything that's flammable. This is becoming a very big thing. It's kind of like you're not really supposed to use your cell phones while doing it. Most people still do. The last thing you want to do is ignite gasoline fumes. That's where dangerous things come in. So the structure of matter, guys, I don't know how many of y'all remember way back when you were in elementary, middle school, or maybe even just high school. But the structure of matter, this is the building blocks for everything, right? So these building blocks we're using atoms. These are composed of the protons, neutrons, and electrons. So if everything is made up of these atoms that create all three of these things, does that mean that everything can technically be electrified? The answer to that is yes. Any and all matter, anything that exists in the universe, can be electrified, or it's part, or some way, somehow, it can become electrical. Does that make sense to everybody? Anybody got any questions on that? All right, so matter is anything that has mass and occupies space. Okay? So that means that even air, because air occupies space, it is a part of matter. So then we talk about molecule. This is the smallest particle that it retains the property of the atom. Okay, again, a lot of this should sound fairly familiar, right? Okay. So when all of the atoms in matter are the same kind, it's an element. There's 92 that occur in nature and are stable. The rest are unstable, which means they only exist momentarily during a reaction. So things like nuclear materials, a lot of that does not exist but for a brief moment. Does that make sense to everybody? So nuclear power is what this is. So the atom is the smallest particle of an element that retains the characteristics of the element. So you have protons, neutrons, and electrons. Protons and neutrons are located strictly in the nucleus. They're located strictly within the nucleus. The electrons, however, are the odd man out. They tend to just kind of float around outside that nucleus. So if you want to think about it this way, protons and neutrons are like the sun in our solar system. The electrons are like the planets. Does that make sense?
Yes, ma'am.
Okay. So the electrons closest to the nucleus have less energy. The ones that orbit, sorry, I'm getting tongue-tied here. The electrons orbit in energy shells that are called electron shells. The last or outermost is called the valence shell, and the valence shell are the ones we like to play with. If your atom has the same number of protons, neutrons, and electrons, it is electrically neutral. However, there are ways to break that bond. So each shell has a maximum number of electrons. So the first can contain 2, the second is up to 8, the third is 18, fourth is 32. These outermost shells cannot have more than 8 electrons at any one time. Let me take that back. It can technically have an extra, but it doesn't do it very well. So generally when you're messing with these, you want a balanced atom. The atom does not want to be unbalanced. So we talk about atomic number. That's the fact that each element has one. The number is the number of protons in the nucleus. Positive charges cancel out negative, so the atom can have its net charge of 0. Is all this making sense to everybody? So then we have, so these are the categories we have to deal with, guys. So we have conductors. These are things that allow current to flow. In that outermost shell, it has 1 to 3 electrons. Does that make sense? So then we have semiconductors. These only have 4 electrons in that outermost shell. And then finally we have insulators. These are used to help prevent current flow and have between 5 and 8 electrons in that outermost shell. So, I'll ask that in a minute. This is something you'll definitely want to memorize. It could very well be a test question. Everybody good? Anybody need a minute?
Thank you.
Okay. So this guy right here, which one of the 3 is he?
Insulator?
He's an insulator, yes. All right, what about the one on the far right?
Conductor?
It's a conductor, and the one in the middle?
Semiconductor.
Semiconductor. Okay? So keep that in mind when we're going through this, guys. So transferring of charges, everybody has done this experiment, if not to yourself, then to somebody else. At the very least, you might have rubbed a balloon on your arms and you saw your arm hair stick up, things like that, yeah? So the reason that happens is we do what's called ionization. These outermost electrons are not very tightly bound to the atom, especially if you've only got 1 to 3 in that outermost shell. It means that they do not have a tight bond. So an electron can gain energy to escape that ring through other methods. Sometimes it's as simple as creating a domino effect. So you start bumping one electron and it goes to the next atom. And it just starts a domino effect and just keeps everything moving. Okay? So the thing we're looking at here is if it loses an electron, it becomes positively charged. If it gains an electron, it becomes negatively charged. Does that make sense to everybody? So in other words, if you have a very negative person around you, if they stick around you, you become very negative. However, if they go off and do their own thing, you become more positive. Does that make sense? Does everybody understand what I'm telling y'all?
Can you explain it again, please?
Okay, so if you've got a negative influence in your life and you decide, or they decide to go away, move away, go do something else, you become a more positive person because you've lost the negative, right? However,
That's right.
if you're the one that gains that negative person, all of a sudden you become very negative. Just to kind of relate it to real world.
That's correct. Yes, ma'am. Thank you.
All right. So copper is the most commonly used in electrical circuits, and because it has only one valence electron. The other really great conductors are things like gold, silver, platinum, the really expensive metals. Those are far more easily able to be used. Matter of fact, a lot of computer parts are made with gold being used, kind of like gold leaf. Very, very thin strips of gold. Okay. So the electrical charge is the fundamental, electrical charge is a fundamental characteristic of protons and electrons. So electrons are what charge?
Negative.
So what is an electron charged as? It is charged as negative, yes. What about protons?
Positive.
It is positive. So opposite charges like to attract and like repel. If it doesn't have a charge, there is nothing to do about that. It just is. So we measure electrical charges in coulombs, which is 6.25 times 10 to the 18th movement of electrons. That is something you might want to write down real quick because that is a very good question. All right. So some terms, we have the electric current, we have circuit, potential difference, resistance, cell, and battery. So electric current is when electrons move. Okay, it is quite literally electricity in motion. And there's two types of flow. There are let's see if I can find it real quick. All right, just giving you an idea. So when you're looking at electron flow, since electrons are a negatively charged particle, right? Electrons are a negatively charged particle, so thus the electrons move from negative to positive. You'll see that? However, the way we have always thought of it is as what is called conventional flow. So what that means is that we tend to perceive it as everything flows from positive to negative instead of negative to positive. Does that make sense?
Miss Bush, what does it mean convention?
So conventional flow is how we think of it versus electron flow is what it actually is.
Okay.
Okay?
Okay.
So
Thank you.
positive flow or conventional flow means that that's how we think it works. It's moving positive to negative. When in fact it's just the opposite. It moves from negative to positive. Does that make sense to everybody?
Yes, ma'am.
Everybody else okay? All right. So circuits, these consist of three main things you have to have. All right, for any circuit, no matter what kind of circuit it is, you have to have three things. You have to have some sort of a source, whether it's voltage, whether it's current, I'm sorry, so if it's voltage, if it's electricity, if it's a generator that's producing voltage, that's one thing. You have to have something to do work, because otherwise, why have you created this if it's not going to do anything, right? All right. So then you also have to have a path for everything to move. So you have to have a source, you have to have a path, and you have to have a load. Does that make sense to everybody?
Yes, ma'am. Like this is the basic one, right?
Yes, this is a very basic circuit. You add a lot more to it over time. So if any of you remember back to elementary or middle school science, I'm not sure when y'all did it, but it's one of those experiments that you end up doing, whereby you take a battery, wires, and a light bulb and use the battery to light the light bulb. Y'all remember doing that?
Yes, ma'am.
It's very, very common, very easy. Little circuit to build. So we use schematics to represent these because having to draw them out is a good idea, simply because if you have to be the one to fix it, you can trace what you did, if that makes any sense. Okay. So a schematic is a graphical representation of a circuit using standardized symbols. So in other words, it's the way we communicate to other people. This is what I'm doing, this is what this does, so that everybody knows what's going on around it. Okay? So this one is a drawn out version. This one is a schematic. So you have the voltage supply for both. And by the way, this is the symbol for a DC voltage source. Okay? So the way we show a DC voltage source, for the negative side, we have the little short line. For the positive side, we have the long line. Okay? Then you have the symbol for a light bulb, and then you have the symbol for the wires that go from the terminals to terminal. Does that make sense to everybody?
Yes, ma'am.
Okay. All right, before we get into the next part, guys, let's take a little bit of a break. All right, so there's two different types of circuits. There's a closed circuit and an open circuit. So the main way I generally explain this to everybody is that a closed circuit acts a lot like a closed bridge. By that I mean, if you've ever seen the big bridges over places like London or some of the other big bridges in movies, whereby you have, let's see if I can get to draw on this. So if you have a bridge, okay, and then right here in the middle, so that boats can get through, they have a way to lift it up so that a boat can go through the channel, right? So this right here, if you have traffic on either side, will make the car traffic stop, simply because it can't go through. So that means that it's an open circuit. So this is whenever your light switch is flipped to the off position. There is no path for flow. Does that make sense? All right. So when the bridge is closed, in other words, the bridge is complete, and you have flow going back and forth over the bridge, that is a closed circuit. That means that everything is moving correctly. Does that make sense to everybody?
Yes, ma'am. Yes, ma'am.
Okay. So an open circuit is no path, a closed circuit is a path. So we have what's called resistance. And this is an element that every electrical circuit has to have. There is no dodging it, I guess you could say. So every electrical pathway has the property of resisting flow. Most wire offers little to no resistance until they have a break in the wire. Last thing you ever really want is a break in the wire. That tends to be rather disastrous. And we'll go over why when we get to the safety portion of this. So with conductance, this is every pathway has an ability to conduct electricity. So conductance and resistance tend to go hand in hand. So this is something you might want to write down in your notes, and that is conductance, which is represented by the letter G, is equal to the inverse of resistance, which is R, as well as the resistance is equal to the inverse of conductance. Does that make sense to everybody? So in other words, if you're looking at something like the dam, like a big dam, right? Everyone knows what I'm talking about? Like the hydroelectric dams. So your conductance is how much water is moving through that dam at any one time to create electricity, as well as to keep the river flowing. With resistance, it's how much of the water is being held back at any one time. Does that make a little more sense?
Yes, ma'am. Yes, ma'am.
So conductance is what it's letting through. Resistance is what's holding it back. Okay. So when it comes to electricity, the very first thing we ever found was what is known as a battery or a cell. Okay. So this is where it is produced by a chemical reaction. So what is in a battery that causes a chemical reaction? Does anybody know? And that is an electrolytic paste, generally some type of acid that allows for that to produce a chemical reaction. So
I thought about acid, but I don't know if the small battery like AAA or AA they have acid too.
all batteries have some form of acid.
All the batteries. Okay.
Most of the time it's sulfuric acid. It's generally sulfuric acid mixed with lead. Okay? A lot of it is sulfuric acid. Okay. All right, so with this one, we have what's called potential difference. Okay, potential difference. And that is where you have so if this is your positive terminal and this is your negative terminal, the thing about potential difference is whatever you end up adding or subtracting, you're going to take the absolute value. Does anybody remember absolute value from elementary, middle school mathematics? Anybody remember it at all? What does the absolute, to taking the absolute value mean, guys? It means that when I take -5 and subtract 3, I should get -8. But the absolute value means that my answer is going to be 8, period. Okay? Does that make sense? So in this case, -5 minus 3, or I can even do, well, that's how that one has to go. You end up with -8, absolute value is 8. So if I have a +2 minus a -10, again, you're going to get a -8, but you take the absolute value and your voltage is 8. Does that make sense?
Yes, ma'am. Always we minus the plus from the.
Yes.
Okay.
All right, so like I said, I'm a bit of a safety nut. I was actually raised in the Alabama power culture, which means that safety is the top priority for everybody to make sure that everybody goes home safe at the end of the day. Safety is a major concern when working with anything, but especially with electricity, because you have the ability to be shocked or burned at any time you're messing with it if you don't treat it with the respect it deserves. So what do I mean by that? Well, when we're kids, we actually are kind of taught to play with electricity because they make all these toys these days that are based on electricity to let you do experiments. Most of those run at a very low voltage. You know, they work on basically a battery. It's not really going to hurt you. But that's where we learn a lot of bad habits when it comes to getting along with electricity. It's not generally a good thing. So, if you are not careful, you can cause all sorts of harm to yourself and to those around you with electricity. You create the potential for fires. How do you do that? You mix electricity with something like insulation and some of the other stuff I've seen. If you really want horror stories, watch something like a home makeover channel where they're finding stuff behind the walls and you have wires that are already trying to burn through wood. Okay. So electrical safety is something you have to take seriously. If not for your sake, then the sake of those around you. Okay. The worst part is that electricity, one of the easiest ways it can kill you is if you let that get across your heart. Why do I say that? Well, because the human body is made up of mostly water, but we also conduct electricity really well. So if, I'm going to draw y'all a little stick figure here. We're going to call him Joe the electrician. And Joe the electrician is working on some wiring up here. And he's not wearing proper PPE. Anybody know what PPE stands for?
Personal protective equipment.
Personal protective equipment. Okay. He's not wearing the proper PPE, so he ends up touching bare wire here and bare wire here. He essentially becomes part of the circuit. So when that electricity, let me change ink colors real quick. So when that electricity starts coming down out of this wire, and it goes trying to go back to, it's going to go two ways. It's going to try and go to ground, and it's going to try and go back up. What is in between your two arms right here that would be really bad to get electricity across?
Your heart.
Your heart. You can stop your heart for doing that. That is not even including the fact that you're going to damage all your other internal organs. Okay? Electricity tends to run very hotly through most people's bodies, and it can and will fry out everything in its path. So that's something you always want to keep in mind dealing with any of this is where is that path going to be, and make sure that you wear proper PPE. Okay? More accidents. What would y'all say causes the most accidents? Let me rephrase that. What is the cause of most accidents?
Carelessness.
Carelessness, that's a big one. What's another?
Complacency.
Complacency, that's a really big one. Not paying attention is probably the biggest reason most people get hurt. Simply because either they've been doing the job forever, so they assume, oh, I'm an expert, I don't need to pay attention to this. Well, that is how people get hurt all the time. It's just because they become complacent. Okay? And this stuff don't play. Okay? So you always really need to be on the lookout as to what it's doing and where you're at and where it's going. Okay. So one of the things I've seen that is, well, let me back up. So one of the things you should never do is you should never disrespect electricity. Always hold it in the highest respect. The whole reason you want to hold it in respect is because it is something that can and will kill you if you decide not to hold that respect out there. Disrespect electricity and it will bite you. Okay? Always be aware of what you're doing so that you don't end up hurting yourself or others. One of the things, if you ever become an electrician, you need to know your codes and why those are there. Most of the time, rules and codes don't get put into law and in place until somebody's gotten hurt or ends up getting killed. So if somebody gives you a rule book that's got all these rules, follow them as closely as you can, because that could very well keep you safe and the people you work with safe. Okay? Everybody good? I said, I'm a safety
Yes,
nut.
ma'am.
I will go ahead and admit I am a safety nut. Simply because there's a lot of people that aren't. So electrical terms. Who's ever heard the term juice? Turn on the juice. Yes, we know what that means, but it is not the correct term. So when you're doing this, use the correct term. If you are talking about the flow of electricity, you're talking about the current. If you're talking about turn on power, say power, things like that. Don't use slang words like turn on the juice. Okay, well, what are you talking about, or, what could possibly be happening that might cause harm to yourself or to others whenever you're dealing with this kind of situation? Communication on any job site is probably the biggest key to making it to where everybody's safe. Is you have to be able to communicate. You have to be able to share what's going on. Say, go turn off the power, I need to work on this, or I'm going to lock out, tag out, and make sure there's nothing running on this. So always make sure you're using correct terms and correct terminology. All right. Any questions on the introduction to electricity, guys? Okay.